Welcome back to another explainer. Today, we're diving into something that's totally invisible to the naked eye, but absolutely vital to literally every single digital device you own. We are talking about the microscopic materials that keep our modern technology from just tearing itself apart under the intense conditions of daily use. Seriously, without this invisible glue, the microchips in your smartphone, your car, your laptop, they just self-destruct. It's a high-stakes, microscopic world, and we're going to break down exactly how it all works.
Okay, let's dive into this. Here is our roadmap. First, we'll look at the microscopic heat problem. Then, we'll explore the three major solutions: capillary underfill, molded underfill, and non-conductive film. And finally, we'll see exactly how engineers choose the right one for the job.
So let's jump right into part one, the microscopic heat problem. To understand the fix, we really have to understand the intense microscopic conflict happening inside every single semiconductor package. Now, this right here is the villain of our story. It's called coefficient of thermal expansion, or CTE mismatch. Here's the deal. When your microchip is running, it generates intense heat, right? Well, the fundamental issue is that a silicon die and the underlying substrate it's attached to are made of totally different materials. So they expand at completely different rates when they get hot. Imagine gluing two sheets of material together, but one is trying to stretch way wider and faster than the other. That creates immense mechanical shear stress on those tiny, fragile flip chip interconnects. You know, the delicate little bumps linking the chip to the board? Just imagine this violent, microscopic tug of war happening thousands of times a second in a space smaller than a grain of rice. Without some kind of underfill material packed into that microscopic gap to lock everything together and absorb that stress, the sheer heat and mechanical pulling would literally cause the chips to destroy their own connections. It is an absolutely mandatory layer of protection. Which brings us to part two, and our baseline hero, capillary underfill, or CUF. This is the classic, proven method for protecting standard flip chip connections. The capillary underfill method is actually this really elegant multi-step process. Step one starts with a post-reflow liquid process, meaning the die is first reflow bonded to the substrate. Then, in step two, a highly fluid liquid epoxy is carefully dispensed right along the edges of the die. Step three is where the magic really happens. Instead of forcefully injecting that liquid, the process relies entirely on capillary action. Think of it kind of like filling a microscopic pothole. The liquid just naturally gets drawn in and flows completely through that ultra-narrow gap under the chip. Finally, step four, it goes into a thermal oven to cure and harden, locking the whole shebang perfectly in place. Now, while CUF is a phenomenal, proven solution for standard single-chip packages, like the processors you'd find in your phone, it definitely has some physical limits. Because it completely relies on fluid flow, it needs a moderate standoff height of roughly 20 to 50 micrometers and a bump pitch that's greater than 80 micrometers. That bump pitch is basically the spacing between the connections. If they are too close together, the fluid just can't squeeze through. This fluid dynamic also creates a voiding risk known as flow front trapping in super dense arrays, where tiny little air bubbles can get trapped as the liquid moves. Plus, you have to leave room on the edge to actually dispense the liquid. That's called a large keep-out zone, and then you have to wait for it to flow. Because of all that, the overall process throughput is actually pretty slow. And that flow time, it just keeps increasing the larger the die gets. Which naturally brings us to a massive manufacturing bottleneck. Look, CUF is reliable, but it is slow. So what if you need to package high-volume modules incredibly fast? What if you're making millions of devices and you literally cannot afford the time it takes for liquid to slowly seep under every single chip? That perfectly sets up part three, molded underfill, or MUF. This is the high-throughput solution engineered specifically to handle the demands of mass production. Molded underfill completely changes the game through something called simultaneous encapsulation. Instead of that multi-step process we just looked at, here, the die is reflowed onto the substrate without any prior underfilling. Then, using transfer or compression molding, a specialized fine filler epoxy mold compound, which is often made of granules or liquid, is forcefully injected. It completely fills that under die gap while simultaneously encapsulating the top and sides of the package in one single lightning-fast step. By knocking out the separate underfill dispense and curing steps, MUF dramatically reduces the unit cost and the total package footprint. It is absolutely perfect for system and package modules where you have multiple components sharing one board. It's efficient, it's scalable, and it uses gang molds to process a bunch of packages at incredibly high speeds. Now, what's really interesting here is the physical limit of the molded underfill process. Even with a fine filler epoxy, you're still forcing a compound into a gap.
So MUF generally requires a moderate to high standoff height of 30 micrometers or more and a bump pitch greater than 60 micrometers. If the gap gets any tighter than that, you run into this severe voiding risk where the mold just doesn't fill the space completely. It literally can't squeeze in. But as we push toward this future of 3D stacked chips, we're looking at needing standoff heights that are less than 15 micrometers. So how on earth do we get the glue in there when the gap is too small for liquid flow and too small for mold injection?
Well, we abandon liquids and molds altogether. Welcome to Part 4, Non-Conductive Film, or NCF. This is the material driving the absolute cutting-edge 3D stacking revolution.
NCF solves both the capillary flow limits and the mold ejection limits by completely reinventing how we apply it. It is a pre-applied solid film process. Instead of messing around with liquids or granules after the chip is placed, a solid epoxy, non-tack resin sheet is laminated directly onto the bumped wafer before it's even diced up into individual chips. Because it doesn't rely on fluid flowing through tight gaps, it entirely bypasses those physical boundaries, which allows for incredibly thin total package heights.
Let's break down how this brilliantly efficient process actually works. Step 1, like we just said, is laminating that solid film right onto the bumped wafer. Then, in Step 2, we use a process called thermocompression bonding, or TCB for short. The TCB tool applies heat and pressure, which temporarily melts that solid film. And then in Step 3, in that exact same rapid motion, the interconnect bumps push right through the melted film to make metallic contact with the substrate below, and the resin immediately cures. All of that happens in one operation. This allows for ultra-fine bump pitches of less than 30 micrometers and very small keep-out zones since the film dimensions are so precise. The only major risk you have to watch out for is solder joint entrapment if the temperature profile slips. But honestly, when it's executed correctly, it's a structural marvel. So we've got 3 radically different approaches to solving the exact same microscopic heat problem. Let's move to Part 5 and synthesize all of this. How do engineers actually decide which underfill is right for the job? So the crucial point here is understanding the technological trade-offs. If you look at bump pitch, CUF handles the largest gaps over 80 micrometers. MUF tightens that down to 60, and then NCF just breaks the barrier entirely, enabling ultra-fine pitches under 30 micrometers. When we talk about throughput, CUF is your slow, steady veteran, whereas both MUF and NCF allow for high-spate manufacturing. MUF through gang molding multiple packages at once, and NCF through that lightning-fast thermocompression bonding. And of course, the voiding risks dictate the failure modes engineers are constantly watching out for. Flow front trapping with those liquids, incomplete fills with the molds, and temperature profile slips causing solder entrapment in the solid films. So, what's the big takeaway for you? Why does this all matter? Well, you're going to use capillary underfill when you're dealing with standard single-chip legacy packages, where equipment flexibility and proven reliability are just way more important than extreme manufacturing speed. You transition over to molded underfill when you absolutely need to pump out high-volume system and package modules, cutting out steps to drastically lower your unit costs. And you bring out the futuristic non-conductive film when you are assembling ultra-fine pitch interconnects, extremely thin dies, or those cutting-edge 3D stacked architectures. I'm talking about things like high bandwidth memory, HBM3 and HBM4, which are literally the chips powering today's most advanced AI processors. It's pretty amazing when you step back and think about it. We have gone from coaxing liquids into tiny gaps to injecting fine filler molds to literally melting solid resin films in a fraction of a second, all just to keep our microchips from destroying themselves. But as the physical limits of semiconductor packaging continue to be pushed and 3D chip stacking gets even denser with gaps approaching near zero, what totally new invisible material are we going to have to invent next? Thank you so much for joining me on this explainer, and I will leave you to ponder that thought until next time. Keep learning and stay focused.